everyone, Shifra back with another notebook. This one is all about statistical testing in Python. Really excited to share this one with all of you because this is what got me interested in data science and data in the first place, just experimental design and all of that jazz. So I want to give a little bit of a reminder to people that all of these notebooks are accompanying season 1 of Saturdata, my podcast by and for the data community, and this is going to be an accompanying resource to the episode on statistical testing. That said, it can also be enjoyed on its own. So if you want to check out the podcast, we'd love to hear what you think. And if not, just this video is totally fine too. So let's get right into it. What we're going to cover in this notebook is statistical analysis and hypothesis testing. And that focuses on SciPy, statistical tests and distributions, hypothesis testing with examples for A/B testing, which is like the practical application of hypothesis testing. We'll also touch on distribution fitting and normality testing, as well as correlation and regression analysis. So prerequisites for this is basic understanding of Marimo, that is the notebook tool that we're using for displaying all this information rather than the more traditional Jupyter notebooks that you might have heard of. We'll expect, basic literacy in Python and the underlying statistical methods that we'll be using. If there's anything that you're not super familiar with, I highly encourage you to pause the video, give it a quick Google search, quick Claude search, and you'll find the resources that you need, the definitions that you need to kind of keep going, because this is all about basically just becoming the most informed, best data professionals that we can meet. So with all of that said, let's get right into it. So we'll start off, of course, by importing all the libraries we're going to need. In this case, it's NumPy, Pandas, Polars, and SciPy stats. With some specific tests so that it's easier to kind of just use them as functions. And we want just some feedback saying that this imported successfully, so we have that. And we'll get into a little bit why we're using both Pandas and Polars for data transformation here, but basically suffice it to say that Pandas is easier to translate to certain SciPy and NumPy processes simply because it's more established, like it's just been around for longer, so it's more compatible with more things. But Polars is definitely the gold standard for data transformation, and the official Saturdata position is that whenever possible, you should use Polars, and then you'll need to translate that into and convert it into Pandas to do certain operations that are only compatible with Pandas data frames, but whenever possible, just, go with it. We're going to start off by generating sample data for our statistical tests, and before we actually generate those NumPy random data sources, we're going to set a NumPy random seed at 42. And just in case people aren't familiar with this, the random seed is kind of giving you a way to define reproducible behavior that's still pseudo-random, meaning that it's gonna appear random to us, but it's going to have the same random pattern every time. If I didn't do this, then every time I reloaded this notebook, the numbers would actually change. But because I have this random seed of 42, it's going to be the same. So if I had a random seed of 1, it would be the same in a different way. Because it's a random seed 42, you can load this notebook at home and you're going to see the same numbers that I'm going to see, which is really valuable for learning and all of the good stuff that we're doing here. And the first thing we're going to do is a 2-sample independent t-test to determine whether there is a statistically significant difference between the means of 2 independent groups. For example, comparing test scores between 2 different classes. And when we talk about independent t-tests, what we're talking about is those 2 different sample groups. If you had a non-independent or paired t-test, you'd be talking about 2 different samples from the same patient in a healthcare study, for example. And independent means the populations are actually different, and that becomes important for different constraints and interpretations of the test. So what we're doing here is we're going to perform the t-test using the stats library here, and we are filling in our group 1 and group 2, that's the random data that we just generated above, from a normal distribution with NumPy functions, and then the output of that is the t-statistic and the p-value. So let's quickly go over what these statistics mean. In this case, the t-statistic is really just measuring the difference between the 2 sample means, so the statistics of group 1 and group 2, and the p-value is measuring what is the likelihood that the null hypothesis would be true given the results that we have. This really low p-value here is telling us that basically the null hypothesis, which in this case would be that the groups are the same, that null hypothesis is really, really unlikely to be true given the drastic result of the t-statistic. Now keep in mind that the t-statistic is basically a measure of how many standard deviations something is away from the mean. So this t-statistic is saying that the results we found are about 3 units away from the mean of the distribution, which means that our results are really far outside standard variability. We typically say that about 99% of the possible data in theoretical distributions falls within 3 standard deviations of the mean, and this is even outside of that. So it's outside like the 99th percentile of expected variability for these two distributions. So that's why the p-value is so low in this case. Typical alpha for a test like this would be 0.05, and we are well below that. Some tests are like 0.049, and you could say, you know, that's really close to the alpha. This is nowhere close to the alpha, so this is a very unambiguous result. What is that result though? Well, the negative t statistic indicates that the first group has a significantly lower mean than the second group, right? With that negative 3.760. With a p-value of essentially 0, we can reject the null hypothesis and conclude that there is a statistically significant difference between the two groups. And what does statistically significant mean here? It means that the difference we see between these groups is not due to random chance. So it doesn't necessarily mean that like this difference is extremely important to a product or to the way we live our life. Like there could be a statistically significant difference between like the amount of water used in pools across 2 cities, but that doesn't have a consequential meaning for our life, right? So statistically significant is very different from practically significant, but it does mean that the difference between these groups is very unlikely to be due to chance. Awesome. So the next test we want to run is a chi-square test, and that is using the stats.chi-square contingency function in SciPy. And that's going to perform a chi-square test of independence, which determines whether there's a statistically significant association between 2 categorical variables in a contingency table. For example, testing if like binary gender is related to product preference, because not every statistical test can account for every different kind of fun non-binary identity, but there we go. And so the reason I'm putting these tests together is that they're 2 versions of the same thing, right? So the t-test that we just did was looking at the statistically significant association or difference between 2 numeric variables with numeric data. And now we're looking at 2 different categorical variables and comparing it in a different modality because it's a different kind of data, categorical versus numeric data here. So what we're doing here is we're creating a 2-dimensional NumPy array, and this is the way that we represent a 2-dimensional data structure in NumPy for those who haven't seen one. So once we have our sample data, we can store the output of this test to different variables. So when we run this test on the data in this shape, we're going to get a chi-square value, a p-value, a degree of freedom value, and an expected number value. The only output that we actually care about though is the chi-square statistic, which is represented as this like chi Greek letter, which is this kind of long X looking thing, and the p-value, which means the same thing as it did before. So with this chi-square value, this test is actually showing no significant association between the categorical variables being tested. The p-value is 329, which is well above the typical alpha 0.05 threshold, and so we can fail to reject the null hypothesis of independence. The null hypothesis is that these 2 variables are very independent of each other. The alternative hypothesis would then be that the variables do depend on each other. And the p-value is the likelihood that the null hypothesis of independence is true given this chi-square statistic of about 2.2. If the p-value is above 0.05, then we pretty much just assume that the null hypothesis is more likely to be true because we have a little bit of evidence for it. And in this case, we're well above that threshold of 0.05, so we are pretty much saying this is evidence for that null hypothesis of independence. The observed frequencies in the contingency table being these observed values here, are not significantly different from what we would expect by chance alone. So that is really what the p-value is saying. All that statistical tests are telling us is this likely to be due to pure chance or not? Awesome. So a lot of times in statistics, we talk about the normal distribution, the bell curve, and we assume a lot of things based on whether we can treat the data as a normal distribution. Once we can treat it as a normal distribution, we can do things like z-statistics, z-standard deviations. We have all these attributes of like, how does the mean relate to the median? And in a normal distribution, they should theoretically be the same. So something that comes up a lot is like, is this data normal or close to normal? And the way that you kind of evaluate for that is the Shapiro-Wilk test for normality. So how do we set this up in code? We again generate some normal data, and this data should be determined to be normal, right? Because it's going to follow a normal distribution. We're generating that using numpy.random.normal with standard arguments here. Great, and then once again, we're going to run the stats package.shapiro, running the first 100 values of the normal data that we generated here. And this is going to return the Shapiro statistic and the Shapiro p-value. And another really cool thing about Marima notebooks is that you can just kind of hover to look at the data types or arguments for the functions that you're using rather, which is really, really helpful. So we again see that the W Shapiro statistic is a 0.978 and the p-value is a 0.085. So let's look at how this is structured, and then we can kind of answer the question of, is this data normal, which we know it will be because once again we generated it from the normal distribution itself. So the Shapiro-Wilk test is assessing whether the data set follows a normal, also known as a Gaussian distribution. So if you ever see the word Gaussian, it's just a fancy word for normal, because the guy who formalized the normal distribution was named Gauss. So just another name for that. And it's comparing the observed data to what would be expected from a perfect normal distribution. The test stat is going to range from 0 to 1, where values closer to 1 indicate better normality. So the W statistic is giving us a number very close to 1, because again, this data is following a normal distribution to the T. So that's exactly what our results show, and our p-value is above the standard alpha of 0.05, so we fail to reject the null hypothesis that the data is normally distributed. And that means we can reasonably assume this data set is following a normal distribution for any statistical analysis that requires that assumption. So when you're being a good data scientist and you're actually looking at the assumptions of all the machine learning algorithms that you want to use, when you evaluate for normality, this is a really good way to do that. Not just looking at the distribution in a visualization, but genuinely testing that normality property. And again, in the real world, we don't always do this because machine learning algorithms are the only tools that we have. So for example, if I have a non-normal data set and someone asks me to do a regression analysis on that data set, linear regression is going to require that my data be normal, but I don't have any other data and I don't have any other methods to make the prediction. So I'm still going to use non-normal data for a method that typically requires normal data, because those are the only tools we have, and my client needs the answer by next week to make a decision at the board meeting, and some prediction is better than nothing. It's better than just blind guessing, in theory. So that is just kind of an unfortunate reality of working in data science, but when you can align your data with your assumptions, that's always a good thing to do. I feel like it's kind of a good time to pause and say that it's really important to know what the null and alternative hypotheses are, so that you know what the p-value that you're getting actually means in the context of those hypotheses. Moral of the story is know the question you're asking, because if you don't know that, then the answer is not very helpful. So always iron out the question you're asking first, and then put that answer in context as much as possible. Great, so the next thing we want to talk about is correlation and basic linear regression using SciPy. As a reminder, linear regression is when we predict y from x. So x is the independent variable and y is the dependent variable because it depends on x. And we are calling it linear regression because we're predicting a line. So we're assuming that y is going to go up or down based on changes in x. And that's how we actually predict those changes in y directly from the changes in x. So what we do first is we create a NumPy array. This is just a one-dimensional array with the numbers 1 to 10, and we store that as our x independent variable data. And then we store the y data using transformations of x while adding a random normal value. So we're basically saying 2 times the x value plus 1 plus some random value between 0 and 1, I believe. And that random value is also following the normal distribution. Same thing we did above for the Shapiro-Wilk test. That's the same way that we are generating that random constant here. So again, similar process to exactly what we did above, where we are just going to run the linear regression function from SciPy using the x and y data as our arguments. And out of that, we get a bunch of useful statistics here. So we get the slope, which is for every change in y, what is the change in x? Rise over run. The intercept, which is when x is 0, what is the y value? That's the y-intercept, where we hit the y-axis on the graph. Then the r value, which is actually a measure of correlation. And then the same p-value we've been looking at is the likelihood that our null hypothesis is true given the observed results. And then we also have a standard error, which is going to tell us how much our model varies on average. I also realized I haven't explained a ton about how we're printing out these variables, just in case people aren't super familiar with Python syntax here. So we're doing a print function here, and inside of that we have what's called the format string. So putting this f string here means that we can throw in variable names. So when we say linear regression slope equals, then brackets are showing that now we're accessing stored variables in our code. We're accessing the slope variable, and this colon.2f is saying that we're printing it with 2 places as a float. And then for this one, we're doing a little transformation here. We're taking the raw R value, we're squaring it to get the R squared, which is the coefficient of determination with 3 floating point decimal places, which hopefully is helpful to people who aren't super familiar with using this syntax. In this case, our slope is 2.05, so every time x moves up 1 unit, y moves up 2.05 units, and the R squared, the coefficient of determination, is the explanatory variable. So this is the correlation coefficient squared, and what this is telling us is what percentage of the change in y can be explained by the change in x. So it's also sometimes called explained variance. Very nerdy, very fun. And in this case, we're seeing a really strong correlation here. Correlation and R squared, it runs between the values of -1 and 1. So in this case, 0 indicates no correlation, -1 indicates a perfect negative correlation, such that every time x moves up, y moves down, and +1 indicates a perfect positive correlation, such that every time x moves up, y also moves up. And in this case, we have 0.942, which is near perfect positive correlation. So in this case, the linear regression is showing us an excellent fit with a strong positive relationship. For every 1 unit increase in the predictor variable x, the response variable y increases by approximately 2.05 units, that's the slope. The R squared equals 0.942 indicates that 94% of the variance in the dependent variable is then explained by the linear relationship between x and y, which is demonstrating a very strong predictive model. So when we talk about goodness of fit, we're saying like, how well does our model, our like modeled line in the linear regression, how well does that actually fit with our data? And in this case, we have a really good fit here. And finally, the p-value of essentially 0 confirms this relationship is highly statistically significant. In this case, the null hypothesis would actually be that the slope, or the change in y based on x, is 0, meaning that the 2 variables are completely independent. But because our slope is 2 and our R squared is so high, close to 1, and our p-value is so close to 0 or virtually 0, we're saying that this is providing evidence for the alternative hypothesis, which is that these variables are related, they are connected, they are correlated, and we can safely reject that null hypothesis saying that they're completely independent in the face of this evidence. So as a reminder, in statistics, we do not prove things, rather we find data that either rejects the null hypothesis or fails to reject the null hypothesis. It's a very kind of negative framed process, which I really love, because what we're saying is we find evidence to refute claims or refute hypotheses, and we never commit and say like, this is the absolute truth. We say, this is the best theory we have based on the evidence present, and if something better comes along, we're always open to that, right? So just a really cool kind of aside on the perspective of statistics and science in general that I absolutely love, and I hope that it's kind of a way for people to connect to the human side of what's going on here. In addition to fitting basic machine learning models to data, we can also fit distributions to data. So if we take some sample data generated from the exponential distribution, which kind of goes like this. So once we have that sample data, we can take the exponential distribution function and we can use something called maximum likelihood estimation that is out of the scope of this video, but feel free to do research for all of you statistical nerds out there. And we can say, what parameters could we come up with to use this exponential function that best models this curve to our sample data? And if we try to do that, we get back some exponential distribution parameters, which are shown here. The stats exponential fit function is returning 2 parameters, location and scale. The first parameter represents the location parameter, essentially the minimum value of our data, which is very close to 0. And the second parameter, this 1.975 here, is the scale parameter lambda, which is closely matching our original exponential parameter of 2 used to generate the data. So in this case, it's kind of an input and output should match type of thing. So because we put this 2 in, we expect to get this lambda 2 out, and we approximate that pretty decently here. So this is confirming that SciPy successfully identified the underlying exponential distribution with the correct rate parameters that we would expect based on our inputs. Awesome. So now I think we want to get into a complete hypothesis testing example and kind of show how we apply this in real life. We're going to use our random seed of 42 again. I think this kind of comes from the fact that 42 is the meaning of life in that nerd book, The Hitchhiker's Guide to the Galaxy, which I actually read last year and I really recommend it. So I think that's why 42 is like always that seed number that we use for these random seeds here. And now what we're going to do is simulate this A/B test data in a very similar way to what we did above in these other examples. So we're essentially going to simulate 2 random sets of data that follows the normal distribution, and we're using slightly different parameters. So 2.3 here, 2.8 here, 0.5 here, 0.6 here. One of these is going to be a control group and one of these is going to be a treatment group. When we look at our sample data, the control group has a mean of 2.248, a standard deviation of 0.452. STD means standard deviation here, guys, does not mean the other thing that you think it means. And then in the treatment group, the mean is 2.813 and the standard deviation is 0.569. So numbers are a little bit high here, and what we want to know is like, is this difference between these groups statistically significant, or does it just look like it's a big difference when really it could be very easily explained by chance, essentially, which is what all of these tests are ultimately testing for here. So to solve this mystery and implement our A/B test, we are going to run a independent two-sample t-test, which is actually the first test we ran in this notebook together, and we're going to get two statistics out of that. We're going to get a t-statistic and a p-value. Then we're going to look at the effect size, which is the mean of the treatment group minus the mean of the control group divided by the square root of the variance of the control group plus the variance of the treatment group divided by 2. And this is kind of how we distribute the difference over the variability of our data sets, right? If the data is highly variable, then the difference doesn't mean as much. If it's not so variable, the difference means more. So we kind of scale to the parameters of our data always. And with that, let's see what are the results of our tests here. So we have this t-statistic, -7.739, and a p-value of 0. And so this is looking like a very strong statistical result here. And when we look at the effect size, or Cohen's d statistic, we get a 1.1. Great. So the t-test here is showing a highly significant difference between the treatment and control groups, with the treatment group performing significantly better. The Cohen's d of 1.1 indicates a large effect size. A d of 0.8 or above is considered large, meaning that the treatment actually produced a substantial practical difference beyond just statistical significance. So as we kind of hammered home in this t-statistic of greater than a magnitude of 7 is pretty outrageous, because we're looking at standard deviations here. And so 3 standard deviations outside the mean is huge, and this is more than double that, right? And then the p-value of 0 is indicating that the hypothesis of there being no statistically significant result here is very unlikely. It's very unlikely that that hypothesis would be true given the t-statistic that we find. So because of that, we have this high effect size. So the t-test results are giving us the statistical significance, and the effect size is kind of giving us the practical significance here. Awesome. We wanted to show one more here, which is a regional sales analysis with statistics tests. So we're going to keep the random seed of 42 like always, and then we can generate some business data, this time with a polars data frame. And this is some sales data following a NumPy random gamma distribution, the marketing spend following a uniform distribution, and then for the region, it's going to randomly choose between north, south, east, west, and for the quarter, it's going to randomly choose between Q1 through Q4 with 500 samples in each of those. So now we have some uniform random data. We can kind of filter and slice and dice this data. So if we look at north and south sales, to do that, all we have to do is take the business data polars data frame and filter that where the region column equals north, and then grab the sales from those filtered values. And then we'll do the same thing for south. So again, business data dot filter, polars column region equals south. It's very self-explanatory. You can read it like English. It reads beautifully. So now we have the north and south sales in their own NumPy arrays here. And so now that we have that data in NumPy format, we can then run statistical tests on it in just one line. So what we're going to do is another independent two-sample t-test on the north and south sales to see, is there a statistically significant difference between the performance of these two different groups here. We're going to run this test on the north and south sales data, and then it's going to return the t-stat and the p-val stat, again using different names for the variables because we can't repeat variable names or reassign variable values, which we love. And in this case, we're seeing a t-statistic of 1.298 and a p-value of 0.195. So in this case, these are not such extreme values. And if we say that, something within 2 standard deviations of the mean is an expected deviation, this t-statistic is not that high, and this p-value is actually telling us that it's above the alpha cutoff of 0.05, which indicates that we failed to reject the null hypothesis, meaning this test comes out for the null hypothesis, such that there is no statistically significant difference between these two groups, which makes sense because they were generated in very similar random ways, right? And with that, we've determined that there's no evidence of a significant difference between these groups. What we have not determined is that there is no difference between the groups. What we're saying is there's no evidence that the difference between the groups is statistically significant. So I think it's important to say that there could be a difference between the statistics. The question is, does that represent the entire population super well? And the answer is it probably doesn't. Awesome. So This entire time we've looked at data for 2 groups at a time, but what if you have multiple groups? What if you have 3 groups? What if you have 5 groups that you are kind of looking at? And that's what ANOVA is for. ANOVA means analysis of variance, and it's really, really good for multiple group comparisons. This is where we're going to be using pandas because it's just easier to work with the ANOVA testing functions when you're using pandas. We're going to use the same business data that we generated above, and we're going to say business PD equals business data dot to pandas, and then we can take the groups of different sales to NumPy using this loop here where we're going to say for each name and group in the business pandas data frame, we're going to group by region, and now we have an array of groups, north, south, east, and west. Awesome. And now that we have all the groups, we can supply that to the one-way ANOVA test, which is going to give us 2 statistics, an F-stat and an ANOVA p-value. So as a little bit of background, you're going to see people talk about a one-way ANOVA and a two-way ANOVA, and basically the simplest way to think of it is that this one-way ANOVA function here is testing the effect of one independent variable on some continuous numerical variables. So in this case, it's what is the effect of each different region on this situation, on these distributions, and we don't have to think about more than one variable at a time because that's out of the scope of this notebook here. So if we print the ANOVA test results, the F statistic is 1.541 and the p-value is 0.203, already looking like we're going to fail to reject the null hypothesis here because, again, that p-value is above 0.05 or any other standard that you'd probably use. So looking at the ANOVA test, it's actually a really interesting test to interpret because there's a lot going on with this F statistic. So the F statistic of 1.541 is actually representing the ratio of variance between each group to the variance within each group. So we can think about how there's differences between north and south, but there's also different areas of north. And so like within the north, there might be a lot of variance. And so we compare the variance across all the groups to the variance within each group. And that can kind of unify and standardize the variance for us. So a value close to 1 would suggest that the variation between each region is similar to the variation within each region. You would expect a higher F statistic, when actually what we see is that the variation across each region is similar to the variation within each region. So it's pretty close to 1 here. And then the p-value, of course, is telling us that we failed to reject our null hypothesis. What is that null hypothesis? So in this case, the null hypothesis would be that each of these regions have the same mean of sales, and the alternative hypothesis would be that at least one region has a different mean from the others. So you could have like 3 that are all the same and 1 that's a bit different. What this p-value means for us is that we failed to reject the null hypothesis that all the means are the same. So essentially what we're saying is all these means are close enough that there's no statistically significant difference between them, meaning even if the means are a bit different, we can attribute all of that to random chance, because that is, again, what statistically significant means. And I feel like at this point, if you watch this video all the way to the end, you can say that with your eyes closed. You can explain that like I'm 5. You can explain that to anyone because we've really, really hammered this point home. So this has been a blast. Let's kind of go through what this notebook demonstrated here. We talked through statistical tests, normality testing, practical hypothesis testing with effect sizes, distribution fitting, regression analysis, and really just seeing how you can use sample data and shape data to supply that to a quick statistical test in SciPy, get your results, and interpret those results. And what you'll see in your data career is it's all about understanding the inputs, outputs, associated hypotheses, so that you can translate those numbers into direct insights that support decisions in your organization. So some key insights for folks: always report your effect size alongside your p-value to understand the practical implications of your results. Statistical significance is, again, not the same as practical significance. There could be a really statistically significant difference in micrometers between this brand of bed sheets and this other brand of bed sheets, and it has no bearing on how we run our business and the decisions that our executives are making. Real-world data might rarely pass our normality tests. It might not be normal, but we still need to proceed anyway with our analysis because machine learning is the only tool that we have to make these predictions. And finally, choose the right test based on your data type and research question. It's crucial to understand what kinds of data you're working with. Is it categorical? Is it independent samples? Is it dependent paired samples? And understand the appropriate test for the data that you have and the question that your research is trying to answer. So with that, thanks for joining, and I'll see you in the next one. Bye!